Today's lecture is about detection transformer. There are two things that I have planned for today. One is understanding the full intuition about detection transformer. And then today we will not be writing detection transformer from scratch, but rather we will be implementing detection transformer for inference. That will be much easier to do. The only difficulty with detection transformer implementation from scratch is not with respect to coding part, it's with respect to accuracy. So it requires long duration of training to get good accuracy. So far in my implementation, the accuracy is very, I would say, pathetic compared to any other previous architectures we have implemented as part of this course. So if the accuracy is really good, I do plan to, if I manage to get good accuracy on any simple data set, like COCO or any other VOC or any data set, I will conduct one lecture on implementation. Otherwise, we'll see. I'll figure out what to do, whether a full from scratch implementation is worth it or not. I'm yet to decide. But in any case, from today's lecture, you will understand detection transformer entirely. And I really want you to pay good attention today because there are some aspects of detection transformer that are easy, but the volume of things that you have to keep in your mind at the same time is a little bit too much. I'm not saying that detection transformer is difficult to understand. Swin was difficult to understand, but detection transformer is easy to understand. It's just that you have to just pay attention to multiple parts at the same time. There is a question whether VLMs are state of the art now. I mean, VLM is a broader term. There are many. VLM is just a term that is used to signify that you want to bring alignment between text and vision. That's all. So state of the art, it depends on the context, right? In the context of detection or in the context of vision and language alignment, or in the context of classification, there are different models that are state of the art. Yeah, I agree. Like implementing from scratch is still worth it, even if accuracy is bad. Yes, I completely agree. So at least I need some respectable accuracy to feel good about it. But let's see. So first of all, what is object detection? Object detection, you might have seen models like YOLO. They are famous models. We'll implement object detection using detection transformer today, but the end goal is to get bounding boxes like this. So these bounding boxes will localize the object. In classification, remember, the whole image is classified. The whole image is set to be labeled A or B or whatever. In detection, we say locally inside this bounding rectangle, there is a person, the class is person, with 64% confidence. Inside this light blue rectangle, there is a dog with 30% confidence and horse with 28% confidence. So here, if you see within one image, you are producing sort of multiple predictions. If this was a classification problem, it would have been, I mean, there are multi-level classification problems, of course, but generally it is conducted for the whole image, not for some localized part of the image. So there are three things we should know. One is we do localization. What do we mean by that? We are able to pinpoint and say that the object of interest is within this rectangle inside the image. We can perform classification. What do I mean by that? Inside this rectangle. So if you now consider that this rectangle is another image, that image now can be classified. We can classify whatever is that in that rectangle to be horse or cat or person or whatever, right? So some type of classification we have to perform. We also have to display some sort of confidence score like this 0.28, 0.3, whatever. So usually object detection models, these are some famous object detection models. Before detection transformer, there were object detection models that purely relied on convolutional neural network. There was no transformer architecture. Some of the models are called YOLO. YOLO is called you only look once. YOLO is the state of the art for real-time fast object detection. Then there are other models like fast RCNN, faster RCNN, RCNN, mask RCNN for drawing mask. So there are many different models for object detection. There is real-time detection transformer, RT DETR. So there are many models for object detection, out of which the models which use transformer in its architecture are like DETR and other variants. So in the whole architecture, the idea is very simple. You have an input image, and the model will try to predict a bounding box. Now, bounding box can be defined using few things, right? Let's say you are given the coordinates of the centroid of this rectangle, and you are given the height and width. You just need how many numbers to represent this rectangle, how many numbers are sufficient for you to draw a rectangle at an exact location in the image. Can you just mention in the chat? 3 or 4. You will need 4 numbers, right? X coordinate of the center, Y coordinate of the center, height of the rectangle, width of the rectangle. So if you have 4 numbers, you can uniquely determine a rectangle. In addition to that, you need what is the class. So whether the class inside that rectangle, whether it's a dog or cat or whatever, what is the confidence score? So all in all, let's say you need sort of like 6 items, right? Class, label, confidence score, width, height, center coordinates in X and Y. Now, if we were to build a naive object detection algorithm without considering YOLO or transformer or anything, just look at what are the input output pairs. Input is in classification, input is an image, output is what? In classification, what is the format of the output? Let's say it's a binary classification. What does it look like? The output look like mathematically? It's not yes or no, right? It's not binary. It's never binary. I mean, classification is supposed to be binary, but you have sort of like a vector with 2 entries, right? You will never have 100% confidence that something is a dog. You will have 99.999%. So your output will be like a vector. In this case, it will be like 0.92 for dog and 0.08 for cat. In this case, it will be 0.15% for cat and 85% for 0.15 for dog, 0.85 for cat. This is label 0. This is label, label number ID1, label ID0, label ID1. So here you say that because the output probability distribution is leaning towards class 0, the object is, or whatever is inside, whatever this image is of class 0. And in this case, this is leaning towards class 1 and class 1 is cat. This is the case if you are performing classification. So essentially think about it. You have some neural network, ignore whether it's a convolutional neural network or whatever. You have some neural network which takes image is bunch of pixels. It takes image as an input and outputs something like a vector, right? At the end of the day. Now, by the same logic, can you think of, so this was about classification problem. So this output is for classification, not for detection. By the same logic, if we were working on detection problem, what could the output vector look like? Oh, one more question before that. Now, this is the prediction, right? This is y cap. And we compare this against something to produce the loss, right? We compare this against ground truth. What does the ground truth look like? Ground truth will look like, in this case, 1, 0. Similarly, this is the y cap prediction for the this image. The ground truth will look like 0, 1 in this case, right? So you compare y cap with y using cross entropy loss. So you can simply say minus yi log pi, where pi is the prediction, yi is the actual label, and sigma I equal to 1 to 2. So here the loss will look like, in this particular case, it will look like minus log E 0.92. In this case, the cross entropy loss will look like minus log 0.85. Because the other term will, although it's a sigma over I equal to 1 to 2, the other term will cancel because it will be 0 multiplied by log of 0.15 plus 1 multiplied by log of 0.85, everything with a negative term, with a negative sign. So this is the loss which we define in classification problem. Now let's forget about classification problem. If we wanted to do something very similar for detection, object detection, let me erase all of this. Just tell me, what should my output look like, or what will my ground truth look like? So let's say this is my input image. What might the ground truth look like? The ground truth, first of all, it will have, let's say, 6 terms, right? we discussed there are 6 terms. One is class. So if dog is of class 0, or rather class 0, yeah. So dog is class 0. The confidence with which this is a dog is 1 for ground truth. We need x, y, width and height. So everything will be normalized between 0 and 1. So let's say the x coordinate and y coordinate of the center is in normalized coordinates is 0.5, 0.5. And let's say height is also like around 60% of the height of the image. So let's say height and width are like 0.65, 0.65, something like this. So now this is y equal to this. This is the ground truth. So this denotes class. So class 0. This denotes probability 1, because this is ground truth. 0.5 is the normalized x coordinate of the center. 0.5 is the normalized y coordinate of the center. 0.65 is the normalized height of the bounding box with respect to the height of the image. 0.65 is again the height of the width of the bounding box with respect to the width of the image. Now the prediction made by neural network, it need not be convolutional neural network. It can be whatever it is. It has to look something like this. It may look like y cap equal to, it will it will not say, okay, by the way, I missed one more term. Maybe I should have 0, 1, 0. Okay, I think this is fine. So this may say something like 0. I should have a probability distribution. So let's add actually 2 terms. So if this is a dog, I will have 0, 1, 0 is the class for dog. So my prediction might look like 0.9 to 0.08. Confidence might be 0.7. Bounding box center coordinates might look like 0.45, 0.3. Height of the bounding box may look like 0.5 and 0.62, whatever. So basically, if my ground truth rectangle is something like this, my actual predicted bounding box will be slightly different. And then same, we can construct loss between these two. There are many different types of losses. The simplest loss you can think of is element-wise subtraction. Take absolute value, add them up. Or element-wise subtraction, take a square, add them up, right? So we can think of many different types of loss functions to construct if we wanted to build a very naive object detection model. But of course, this has a lot of limitations, because here this can only detect one object in the image. What if my image had 2 dogs? Like the example image which I showed here, there were 3 objects in this image. So then my dimension, right now this has what? 1, 2, 3, 4, 5, 6, 7 dimensions. It's like 7 by 1. But what if I had 2 objects, 2 different type of objects? What if I had multiple objects of the same class? Then there are many such issues that this vanilla or naive object detection model algorithm cannot take care of. But that is okay, because here the point is just to make you understand or make you think about, okay, what may this object detection model look like if you were to build something completely from scratch without transformer, without anything, right? You will simply have an input image. You will have some sort of neural network with or without convolution. With convolution means, of course, you will have better feature extraction. And then output, you will get one vector. That vector you will compare with your ground truth. Okay, so now this is the basic of how, if you were to build an object detection model for the first time in the history of computer vision, this is maybe what you may try in the very beginning. But people have already tried it. There are other good models like YOLO, which does take care of some of the problems which I mentioned. If there are small objects inside the image, if there are multiple objects inside the image, how those things are taken care of. I have conducted detailed lectures on this as part of one of the courses earlier. So if you are interested in that, check that out. But in any case, we are going to discuss detection transformer right now. So detection transformer, again, as name suggests, it's for object detection with the help of transformers. Now you may wonder, does it mean that there is no convolution operation involved? There is actually convolution operation also involved, but transformer plays a huge role. In fact, there are two types of transformer here: transformer encoder and transformer decoder. We will see all of that. The paper is from Facebook AI in 2020. It has 21K citations. So it's like a highly cited paper. You will still see detection transformer models being used for inference. So the paper makes some claims meaning why the paper is better than some of the earlier techniques that existed. So some of the earlier techniques depended on something called as anchor boxes. I will define what anchor boxes is. Even if you don't fully understand what exactly are anchor boxes, it will not affect your understanding of today's lecture. But I'm just saying, in case you plan to read the paper, when you read about anchor boxes in the paper, I just want you to visualize something. I will show you what that is. So this detection transformer eliminates the need for anchor boxes. It also eliminates the need for something called as non-maximum suppression. So maybe you should also understand what is non-maximum suppression. Even if you don't understand, you will fully understand detection transformer. But when you read the paper, you may wonder what is non-maximum suppression. So let's discuss briefly about these two things, and then we will look at the architecture. So some models, like later models of RCNN, faster RCNN, for example, what they did was, instead of directly predicting a bounding rectangle out of the blue, instead of directly saying, hey, here is my bounding rectangle, what they did was they predefined bunch of anchor points. So here you can see these crosses. These are all anchor points aligned like a nice grid. And around these anchor points, they defined 9 anchor boxes. So these yellow boxes are actually 9 boxes overlapped on top of each other. And these boxes came in different sizes and different aspect ratios. Some boxes are more like square. For example, like this is more like a square one. But this one, for example, has a lean aspect ratio. This one has a lean aspect ratio. So the reason why anchor boxes were defined was because what you can do if you start with anchor boxes is you can simply modify the size and position of the anchor box little bit. So you try to modify the height of this anchor box by 10% and width by 5% and center coordinates by 2% in certain direction, and see whether the anchor box is moving closer and closer towards your ground truth in the training. And you do that for all anchor boxes for all the anchors. So essentially what happens is you will be able to make predictions for objects with weird aspect ratios. So weird aspect ratio meaning, see, this is a phone. And this one, if I'm holding it like this, it has a certain aspect ratio. But then if I'm holding it like this, it's the same object, but now the aspect ratio has completely changed. So earlier object detection models has had issues with extremely high values of aspect ratios or extremely low values of aspect ratios, because and that may happen in reality. Aspect ratio fully depends on from which angle you are looking at the object. So if the same camel, if you are looking at from the front or back, it will look like lean, its aspect ratio will be higher. So what they did was, by defining these anchor points, which are starting points, and by defining these anchor boxes as starting boxes, and by modifying those boxes little by little by little during the training, you can come up with good predictions, good bounding box predictions, which are closer and closer to the ground truth. So this was one idea. For the purpose of today's lecture, you don't have to understand how exactly the modification is done. I will simply say modification was done using some sort of regression. So you regress the height, width, center coordinates little by little to make the box better and better. Does it mean that it can detect 9 objects only for 9 anchor boxes? So the entire image will not have only 9 anchor boxes. It will have 9 multiplied by how many ever anchor points are there. So these anchor boxes are all centered around this point. So this grid is like a very nice grid. So grid is predefined. Anchor boxes are also starting points of anchor boxes are also predefined. So total number of anchor boxes in the starting will be 9 multiplied by whatever is the number of grid points. So you will start from that as the starting point, and then you will try to modify the shape and position of anchor boxes and try to see which anchor boxes are correlating the best with ground truth. So this is what is done in the training, but I'll come to some problems with that. So this was a complex algorithm, of course, but all I want to take away from this is previous algorithms relied a lot on hand engineered anchor boxes. Already you have asked question, how many anchor boxes? It's decided by human. What should be the aspect ratio of these anchor boxes? Again, decided by human. So these are all hand engineered aspects of the previous algorithms before detection transformer. One more thing which I want to mention is, so anchor boxes detection transformer managed to eliminate. That is one point. Just keep it in your mind. This will not affect your understanding of detection transformer. Second thing is, it also eliminated the need for something called as non-maximum suppression. Now, this part is kind of easy to understand. So non-maximum suppression simply means, let me skip this and I'll just draw and show you something. Let's say you are running a detection transformer algorithm during inference, okay? Now, if you are using a model which has anchor boxes, what will happen is you will make predictions. You will make boxes that are predictions. And let's say you have one box like this and another box that looks like this. Then you have another set of two boxes that look like this. Okay. So this is your whole prediction. Now, this is my image. My image is this big rectangle. Let me just fill something. Okay. So think about this. If I have an image and if I have 4 boxes in the final prediction, what should I conclude from this? Should I conclude that there are 4 objects in this image? Is that the conclusion that I should come up with by looking at the fact that there are 4 predicted boxes? Not necessarily. The reason is maybe there are multiple anchor boxes that evolved to predict objects like that are duplicates. Duplicates as in this box is predicting object A. This is also predicting object A. This box is predicting object B. This is also predicting object B. Now, how do you know that? Because in inference, you don't know how many objects are there. You are just passing an image. There is no ground truth available to you, right? You simply have a bunch of anchor boxes and you have ground truth. You don't have ground truth. Now you have to tell how many objects are there and which are the anchor boxes that correspond to your object. So to do this is why people introduced the algorithm called non-maximum suppression. So let's go through the algorithm steps one by one, and then we'll come back to this and you will understand what is the algorithm. So non-maximum suppression starts like this. So firstly, we don't just predict bounding boxes. We also predict boxes with confidence score, right? So this box may have a confidence score of 0.9. Maybe this has confidence score of 0.3. Maybe this is predicted with 0.85. This is with 0.7. So boxes are associated with confidence score. So first thing is you sort the boxes based on confidence score. So if you predicted 4 boxes, you sort the boxes based on confidence score, but at the same time, you remove certain boxes with very low confidence because you anyway don't care about low confidence predictions. Because if you reduce your confidence threshold, maybe you will get 100 boxes. Maybe 90 of those boxes are with 10% confidence. So if your model is telling you that, hey, there is a bounding box in this particular location of the image, but I'm only 10% confident that there is an image inside this box. Will you take that box or not? You don't care about that box. You don't care about low confidence predictions. So first is you remove low confidence boxes below a certain threshold. So first problem here is, how is this threshold decided? Again, it is human engineered. People decided. It's not based on first principles. It's based on simple trial and error. So people will decide, okay, I don't want to consider any boxes below 0.3 or 0.5 confidence score. Then among the remaining boxes, you sort those boxes. Now let's go back to our example. So in this case, let's say my confidence threshold was 0.3. It should be above 0.3. Then what will happen is naturally this box will be eliminated. So this box is now not even in the question. Now I have 3 boxes, a box with 0.9 score, a box with 0.85 score, and a box with 0.7 as the confidence score. Now what do we do? Now I want to figure out, just based on mathematics, which are the boxes that now I should retain. Now what we do is we first pick the box with the highest confidence. So in our case, the box with highest confidence was the one with 0.9. So now this is the box with the highest confidence. All right. this 0.9. The second highest confidence guy is this 0.85, this box. So now what we have to do is we pick the box with the highest confidence, and let's call that as B1. That will be a contender in our final output list, meaning the box with the highest confidence will be one of the boxes that we will consider to be a good prediction. But then what we will do is we will compare this B1 with the remaining boxes. So now let's compare B1 with the remaining boxes. So B1 is compared with, so this is B1, okay? And let's say this is B2 and this is B3. So now B1 will enter our final list. We'll say B1 is our highest confidence box. So that is retained. We are not removing it. But now B1 and B2 are compared, and B1 and B3 are compared. Can you tell me what is IOU? First of all, IOU is a term that is used to define how much these boxes overlap with each other. So IOU is called intersection over union. I'll show you a figure. So IOU is area of intersection divided by area of union. So this area divided by this blue shaded area. If two boxes are having zero overlap, IOU will be equal to 0. If two boxes are overlapping perfectly, IOU will be equal to 1. If the overlap is in between, IOU will be somewhere in between. Now think about this. If IOU between B1 and another box is extremely low, okay, let's consider two boxes. Don't think about B2, B3, but let's say B1, I have box B1 and Bn. And let's say IOU between these boxes are like 0.1 or 0.2 or something like this. Okay. What we want to predict is we want to predict unique, high confidence boxes, unique boxes that have high confidence, because we want to predict unique objects. Now, my question is, we already rejected all the low confidence boxes. So every box is below 0.3 confidence is removed already. And now B1 is our highest confidence box. Bn is our nth box. In terms of confidence descending order, Bn is the nth box. And what I'm telling you is IOU between B1 and Bn is somewhere between 0.1 to 0.2. We already decided that B1 we are not neglecting. B1 is part of our final prediction because B1 is our highest confidence box. My question is, based on IOU, will you eliminate Bn or will you keep Bn? That's my question. For those of you who said keep Bn, why do you say you should keep Bn? Because B1 and Bn are anyway both kind of high confidence boxes, because low confidence boxes are removed. And the overlap between B1 and Bn is very low, which means it's very highly likely that box B1 and box Bn are bounding boxes around two different objects, not around the same objects. So B1 and Bn are not duplicate predictions of the same objects. They are very likely different objects being predicted. But what if B1 and Bn had, so here itself, just look at the example. What is the IOU between B1 and B2? IOU between B1 and B2 is 0. IOU between B1 and B3 is 0. Now, those of you who said eliminate B1 based on low IOU score, think about this. Will you eliminate B2 compared to B1? If you are comparing between B1 and B2, will you eliminate B2? You will not eliminate B2 because B2 is probably predicting completely different object altogether. B3 is predicting completely different object altogether, right? So what you do is you look at B1 compared with every other boxes. If there is a box which has high overlap with B1, so for example, let's say the confidence of this guy was not 0.3, let's say this was 0.7, right? Then overlap between B1 and let me call this as B4 for simplicity. If B1 and B4 are compared, their IOU is very high because the intersection is this much. Union is not so much higher than intersection. So IOU is very high score, which means B4 will get eliminated in the process. B2 and B3 will not get eliminated because when you compare B1 with B2 and when you compare B1 with B3, there is no overlap between them. So based on IOU, they are not going to get eliminated. However, this step we have to repeat again. Now B4 is eliminated. B1 is already finalized. Then you look at the remaining boxes. Now, what are the remaining boxes? B1 is already finalized. B4 is eliminated. Now you have B2 and B3 to look at. Now, which is the highest confidence box among these remaining ones? B2 is the highest confidence box. Then you compare between B2 and B3. So I'll explain once again. Your goal is to eliminate duplicate boxes. Why? Because you only want one bounding box around one object. You don't want two bounding boxes around the same object. Now, when during inference, anchors are getting converted to predicted boxes, which means there may be multiple boxes that may look like similar. There will be multiple other boxes which are different from some other boxes. So now you have to predict which boxes are actually not duplicates, which are the actual boxes that you care about. So first you look at the confidence scores of every box. You sort the boxes in terms of confidence score. You eliminate all the boxes with low confidence because you don't care about low confidence predictions. Then among the rest of the high confidence boxes, you pick the highest confidence guy and finalize it. So here the highest confidence box was B1. So B1 you are not going to eliminate. Now you compare every other box which are remaining with B1, and whichever boxes have very high overlap with B1. And how do you define very high overlap? Whichever boxes have a threshold above IOU value with B1, you eliminate those boxes because whichever boxes have very high overlap with B1 are likely duplicate boxes, as you can see in this image. Here B1 and B4 are probably predicting a person, probably bounding boxes around the person. B2 and B3 are probably boxes around a cat. But you don't need two boxes to predict one object. You need one box to predict one object, and you want the best box. You don't want the second best box. So now what you do, you compare B1 with B2, B3, and B4. And you see that B1 and B4 have very high intersection over union. Maybe IOU score is 0.8. I don't have the exact numbers, but you can see that intersection between B1 and B4 is very high, which means IOU between B1 and B4 is very high. And that for that reason, you eliminate B4. Why? Because B4 is very likely a duplicate box that is predicting what B1 has already predicted, but at a lower confidence. Now, once B4 is eliminated and B1 is finalized, now you look at the rest of the boxes. What are the remaining boxes now? Remaining boxes are B2 and B3. From the remaining boxes, again, just like how you picked B1 because it has high confidence, you pick from the remaining boxes the highest confidence box. What is the highest confidence box now? B2. B2 has 85% confidence. Now you again repeat the same thing. B2 and B3 you compare. Does B2 and B3 overlap significantly? Yes. Which means should you eliminate B3? Yes, you should eliminate B3. But if you had another box called B5, let's say this was B5, will B5 get eliminated? And let's say the confidence here was 0.6. Will B5 get eliminated when it was compared against B1? It will not get eliminated because it has no overlap. Will B5 get eliminated when it gets compared against B2? It will not get eliminated. You don't know whether there is an object here or not because you are doing inference. You don't have ground truth. You can visually see, of course, but algorithm does not know. Algorithm just knows which boxes are far apart and which boxes are duplicates that are not far apart, which are confident boxes and which are not confident boxes. So B1 is when it is compared against all the other boxes, B4 will get eliminated because B1 and B4 has very high overlap. Then we will move to B2 because B1 is finalized, B4 is gone. Then next highest confidence box is B2. If B2 is compared against B3 and B5, B5 will not get eliminated, but B3 will get eliminated. Now what is remaining is only B2 and B5 and B1. B2 is finalized and only thing that is remaining is B5. B5, there is nothing to compare against it and its confidence score is anyway higher than our threshold. So among the 5 boxes that were predicted, only B1, B2 and B5 will survive. B4 and B3 will be eliminated. These are called non-maximum, basically non-maximum suppression. So the NMS is basically, it's almost like a hand engineered technique. Where is the hand engineering coming? In 2 places, in deciding the confidence threshold and in deciding the IOU threshold. The numbers which are used for the threshold here are simply hand engineered, meaning we humans decide. It's not coming from any foundational idea. It's just a human engineered technique. So this NMS was one way to first predict large number of boxes and then eliminate boxes that are duplicates, right? And this was being used in many architectures before. And detection transformer very cleverly eliminates this non-maximum suppression. It also eliminates anchors. So we will see if non-maximum suppression is, if anchors are not used, then what else is being used in detection transformer, that we will see. So detection transformer actually uses a word called direct set prediction. So if you look at the abstract of the paper, somewhere they are mentioning, we consider this as a direct set prediction problem. Or a set-based global loss. Somewhere in the introduction or somewhere in the abstract, they make use of this term called direct set prediction. So essentially what direct set prediction means, detection transformer will predict always a certain number of objects. So the number of objects is always fixed. So in the actual detection transformer paper, I think it was 100. So it will predict 100 objects, always, irrespective of what image you feed. Now you might think, what if in my image there is only one object? Then what happens is, out of the 100 bounding box rectangles that detection transformer predicts, only one will correspond to the object. Remaining 99 will correspond to background. So basically, there will be 100 boxes that are predicted. Only one will enclose the object properly. Remaining will be enclosing places in the background. So what do we mean by background? Isn't everything background? But background is something like this. So here, if camel is the object, this is how the one box which correspond to object will look like. And these are all boxes that are basically background. So detection transformer, what it does is, first, in an image, first of all, we don't care about predicting thousands of objects. So we have to first decide maximum how many objects are we interested to predict in any image. Maybe 20, 5, 50, something like that, right? We normally don't want to draw 1,000 bounding boxes around inside an image because it's not useful. So firstly, detection transformer decided that, okay, so I will say the maximum number of objects that I am going to predict is 100. And then, so that is called as a set. So it is predicting a set of 100 bounding boxes. And not just that, it can, because this 100 is a much higher number than the potential number of objects that will be present in an image, it doesn't matter whether in your actual image, whether there are 3 objects or 5 objects or 6 objects. So for example, in this image, there are 2 camels actually. So what will detection transformer prediction look like? It will look like there will be 2 boxes. There will be 2 boxes, one around camel number 1, another around camel number 2. And rest of the boxes will actually be such that they are in the background. They will be boxes which are enclosing pixels that are part of the background. So there will be 98 such boxes. So this 100 number was again a little bit not arbitrary. It was chosen because maybe in most of the object detection data sets, you don't encounter large number of objects per image. Here, there are no anchor boxes, by the way. Here in detection transformer, there is no concept of anchor box. I will tell how the box prediction happens. But basically, in detection transformer, the predicted boxes, you can have variable number of objects. And this variable can be anywhere between 0 to 100. The boxes can be with any shape, any aspect ratio, at any position. And we will see how this prediction is done. So the reason why it says direct set prediction is, detection transformer does not start from a certain set of anchors and then changing the anchor values through regression and then eliminating some of those modified anchors using non-maximum suppression. None of that is done. It predicts a certain set of number of boxes, and it tries to match each box to a unique object. If the number of objects is less than 100, which will be in most cases, of course, what it will do is 5 unique boxes will be, let's say 5 is the number of objects. 5 uniquely predicted boxes will be assigned to those unique objects. Remaining 95 boxes will be assigned to background. Now, there are a few things which you can only understand when we visualize this whole process. So that is what we are going to do. And you may also have, I'm sure at this point you have a bunch of questions, like how does the box matching look like? What is the ground truth? How are the predictions matched with the ground truth? how is the loss function constructed. So there is a very interesting loss function, which is probably one of the most interesting loss functions that I have recently come across, called Hungarian loss function, Hungarian matching. Hungarian algorithm is something that has existed before, much before deep learning. So we'll also understand in today's lecture what exactly is this Hungarian matching. So I have dumped a bunch of terms on you right now. I'm aware of it, but we will go through it sequentially. So I have dumped the term NMS, anchor boxes, Hungarian matching, set prediction. So don't worry about all of this. I hope anchor and NMS is somewhat clear. Now we'll come to what exactly does detection transformer do with respect to architecture. So now we come to the architecture of the detection transformer. So first I will show you the diagrams from the paper. So this is from the paper figure 1. It's simple, but it may look intimidating, but I'll go through it step by step. In the first step, you have input image. In the second step, you have a backbone CNN. So this is where convolution operation comes into picture. This convolution operation is used for extracting spatial features from the input image. Then those features are passed through two blocks, one with transformer encoder and one with decoder. We'll get into the details of this, but this is just an overview. Okay, so this image is just an overview, bird's eye view, BEV. Input image, CNN backbone, like ResNet 50 or ResNet 100, pre-trained. So this is a pre-trained CNN, okay, pre-trained on ImageNet or any other dataset. It extracts the features. Those features are passed, tokenized and passed through transformer encoder and decoder. We will see how this looks like. And then it predicts this set of boxes. How many sets? 100 or whatever the number we decide. But basically that number will be fixed. And then what they are showing here is, just zoom in on this image. Here, actually, there are totally 2 boxes in the ground truth. So this is the ground truth. So you only need 2 boxes. So look at the color here. So what has happened is, what is this image trying to show is, this box and this box, this red box and yellow box will be matched to ground truth objects. This will be matched to background. So because this green is a background box. For the rest of the, and these are actually something called queries. So I'll come to that. Just remember the term. These are called object queries. I will come to the details of all of this, but just focus on what is happening. Each object query is corresponding to either a box or no box. No box meaning no object. So here, this black color query, blue color query, and yellow, or this, whatever this color is, that query is corresponding to no box or no object. This green color query is corresponding to the background box. This red and yellow color query are corresponding to the object boxes. So these are the 2 objects that we are looking at. So somehow what we are trying to do is, we are teaching these queries to predict the appropriate boxes. We will see the details. So just understand this much first. From an overview, maybe we can say there are 4 parts. Part 1 is the CNN. Part 2 and 3 are the transformer encoder and decoder. Part 4 is where this matching happens. So now we look at this sequentially. So first is, we have to discuss about this set prediction, what this direct set prediction problem. How does the input look like? What the model looks like? What does the output look like? And what is this Hungarian loss function or Hungarian matching? If we understand all of these things, we can understand the whole model. Now, this is another image, which is slightly, it is still zoomed out, but not as zoomed out as the previous image. I think this was the figure 2 of the paper. So here, what it starts, I mean, it's showing the same thing essentially, the CNN backbone, feature extraction. Then this features to the features which are tokenized, you add position embedding. We'll come to the position embedding. There are some details which you should notice about the position embedding, but I have my own versions of the figure, which in my opinion is a bit easier to understand. Then you have, so this is part 1, backbone, part 2, encoder, part 3, decoder, and part 4, prediction heads. Now, we have to go a bit more slower. We have to go through this part by part, but just try to understand that decoder does something where object queries are initialized here. Encoder does something where the tokens that are coming from image features are converted to context vectors. Okay, just broad level, in broad level, just think about these things. Details we are yet to look at. We'll look at it in a moment. And then prediction heads will take care of converting these transformed object queries into predicted boxes. All right, so now let's look at detection transformer architecture in parts. So first part, you convert your input image through ResNet 50 or ResNet 101 retrained neural network into feature map. Feature map will have certain height, certain width, certain number of channels C. In general, you might have seen that here there will be some height, width, and 3 channels, RGB. But features typically will have lower spatial resolution, more number of channels, maybe 64 channels or 128 channels. This is what you have seen generally. So feature map, whenever we hear about feature map, you have to imagine a multi-channel feature map, okay, not just one channel. Usually this will be large number of channels. So you're taking abstract features from the image and you are trying to make use of those features for your prediction. So part 1 is probably the most straightforward part because we have discussed this many times about transformer architecture. Now, part 2, not transformer, about CNN architecture. Now, part 2 is where we have encoder, transformer encoder. Now, transformer encoder also, this part needs to be zoomed in. We will look at this in a zoomed in view in some time. But in general, you know what is a transformer encoder. It will have a bunch of transformer blocks. Each transformer block will have layer normalization, multi-layer perceptron, residual connections, multi-layer perceptron, multi-head attention, residual connections, again layer normalization, again multi-layer perceptron, again residual connection. This whole thing enclosed in one single thing, which I will show you as an image. But basically, that is what is there in one transformer block. And those blocks are added in series inside the transformer encoder. I will zoom this in and show you in a bit. But right now we are zooming out slightly. So feature map is first converted into sequence of grid cells. So you convert the grids, each grid cell of multi-channels into single channel. You convert almost like patches converted to tokens. So here you have sequence of tokens. Now, what are these tokens converted into through transformer encoder? These tokens are converted into context vectors. So each token will be converted to corresponding context vector. Now, these context vectors are much richer in information, right? This is just like how transformer for Envision transformer or in any other transformer works. So feature map is, yes, feature map is flattened. It is divided into certain cells and it is flattened. But the number of here itself, it has a certain height, width, and number of channels. So by the time it reaches here, what is done is h comma width comma embedding dimension, or I can call it as B. So basically, the total number of vectors will be h times W, and the dimensionality of each vector will be D, where D is the embedding dimension in the in my transformer encoder. So basically, extract feature map using CNN, convert the dimensionality into whatever dimensionality is used in the transformer, and then convert the feature map into sequence. Converting into patches are not required because already the feature map is of very low spatial resolution. So I just drew these grid lines just to make you understand that whatever is there, it's like converted into a sequence, right? You are not explicitly converting to patches. Converting to patches would have been required if you are starting with an input image with high spatial resolution. Here you can directly, the total number, you can assume that each patch is 1 by 1 in resolution. So yeah, I mean, in a sense, it's patchifying, but only 1 pixel per patch, 1 by 1, something like that. But what you are doing here is you are converting the feature map, which was looking like H, W, C, where C is the number of channels. You project it through a projection layer to convert into H, W, D, where D is the embedding dimension. So now you will say you have H times W, that many grid cells in the sequence, and the dimensionality of each of those will be D dimensionality. So you have now tokens, H by W number of tokens, and then you have D as the dimensionality of each of those tokens. What happens to tokens when it passes through transformer encoder? Tokens are converted to context vectors. And inside this transformer encoder, there are multiple transformer blocks. Okay, transformer block number 1, block number 2, n number of transformer blocks. So basically, it will become a richer and richer context vector. So this is roughly what happens in transformer encoder. We will look at this in a slightly more detail in a little bit. Now, part 3. So now this is the output which you get from the transformer encoder, right? So of course, this output has to go into the input of transformer decoder. Where else have you seen encoder, decoder? In the attention is all you need paper. You might remember left side was encoder and right side was decoder over here. So this, let me copy paste this. So this left side is encoder, right side is decoder. So basically this paper was released not so far away from attention is all you need paper. Now in part 3, you have actually 2 inputs. So transformer decoder is part 3. It has 2 types of inputs. One type of input is called object query. Another set of input is whatever output comes from the encoder. So what is the output that comes from the encoder? This guy. These context vectors corresponding to your grid cells. So they are coming here. They are one set of input into the transformer decoder. Another set of input is object query. Just like this, where is the attention is all you need. Let me paste it once more. So here, look at this. Inside the decoder, into this multi-head attention, there are 2 types of input coming. One input is coming from this part of the decoder, as you can see here, and this is the query. 2 inputs are coming from the output of the encoder. This is the output of the encoder, and this is key, and this is value. I will explain this in a bit more detail, but I'm just first showing you the parallel between transformer, encoder, decoder, and attention is all you need, and here. But I plan to go into details of this. So don't worry if you don't understand some things very clearly. I know you have not understood something very clearly because I'm yet to show you the fully expanded figure. But just focus on decoder. So decoder takes encoder output as one set of inputs, and it begins with object queries. Now, why are we calling this as object queries, and what are these? So these are initialized as 0 vectors of dimensionality same as that of the dimensionality of the embedding space. So if your embedding space is, let's say, 768 dimensions, these object queries are a bunch of vectors initialized as zeros, and they are also, by the way, learnable. So the values of those vectors will be learnable through training. But now the more important thing that you have to notice is that the number of bounding boxes that you predict, including, and when I say number of bounding boxes, I'm also counting no object. So boxes plus no object or null. So this is called null box or phi. I don't even know if it is right to call it as a box, but number of boxes plus these null objects, the total number of these that are predicted will be equal to, according to this diagram, it will be 5. So how many ever number of queries you have, that is the maximum number of objects your model will be able to predict. So now if you have, 4 in this case, my bad. Now, if you want to predict 100 objects maximum, you should start with 100 object queries. Okay. So that is the first thing to notice. So the number of objects that you can maximum predict in your image will depend on the number of object queries that you have, which means these queries are now somehow getting transformed into bounding boxes. Okay, so that is now what we are going to see. So just let me reiterate that sentence. Object queries, which are vectors of same dimensionality as that of the embedding dimension inside the transformer encoder decoder blocks, those object queries are now responsible for transforming themselves into the bounding boxes. Some might be actual bounding boxes, some might be null boxes, which predict no object. Now you should have some questions. Now, what about encoder output? Because in encoder output, actually the number of tokens are, let's say, dependent on the feature map spatial dimension. So let's say the number of tokens that are there here is 20. So here, how many tokens will come? How many context vectors will come? A sequence of 20 context vectors will come. But here, the number of queries that are coming are 4, right? So far, this we have never discussed in this course. So far, whenever we constructed attention was query.key transpose divided by square root of D, softmax of this, multiplied by value. This is how we constructed attention. In all the cases that we have discussed so far, as far as I remember, the number of tokens, you had a sequence. So let's say the dog chased the ball or something. You had a sequence which was converted to tokens. So here you have 5 tokens. This token was converted to query key value. This token was converted to query key value. This was converted to query key value, right? So the total number of queries and keys were exactly the same. So here you have 1, 2, 3, 4, 5 queries and 5 keys. But here suddenly you are seeing there are actually 4 queries. So number of object queries are 4. But here the context vector has now the 20 tokens in its sequence, right? So how do you deal with this? So keep this question in your mind. We are going to look at it. Okay. So just let me step back. Part 1 is ResNet backbone. ResNet backbone will extract features. Part 2 is where features are tokenized. Those tokens are passed through transformer encoder to be converted into context vectors. Those context vectors, along with object queries, are fed into the transformer decoder. And transformer decoder will do something. We are yet to see what is that. It will do something to convert the object queries, of course, with the help of encoder output, because this has to be used. But transformer decoder will convert the object queries into bounding box predictions somehow. So now that is the last part. So last part is these object queries converted into bounding box predictions through multi-layer perceptron. So this FFN is feed-forward network, but basically it's a multi-layer perceptron which will predict 2 things. So actually there are 2 multi-layer perceptrons. Here, the way I have drawn it, which is very similar to the way the people have drawn this image in the paper, will make it look as if there are 4 feed-forward neural networks. That's not the case. There are actually only 2 feed-forward neural network. So this is MLP for predicting class, and this is MLP for predicting box. So these 4 object queries will pass through these 2 multi-layer perceptrons. So this class MLP is responsible for saying whether this box is responsible for whether that box is corresponding to cat or background or something else. Yes, I'll come to object query because I have to spend a bit more time in object query. But let me show you this last part and then we'll zoom in a little bit. The class MLP is responsible for saying whether object query 1, object query 2, 3, etc. are corresponding to cat, dog, background, etc. MLP for box is responsible for drawing the box. So whether that corresponding box is in this position or slightly to the left or slightly to the right, etc. Okay. So totally 4 parts. Part 1 for extracting features, part 2 for converting extracted features to context vectors, part 3 for converting queries with the help of context vectors into better representations, which is using a transformer decoder, and part 4 for predicting objects using the transformed object queries. Now we have a bunch of things to discuss here. Where is the loss function? What are these object queries exactly? How does the multi-layer perceptron look like? Where is position embedding added? There are a bunch of questions. So we have to go through all of that. Right now, this is just a high-level overview. And at the end, if there are 4 boxes predicted, right, we have to compare it with the ground truth. So we have to figure out what kind of loss function are we going to construct. So at the moment, okay, let me zoom out and just show you this overall. This is just combining the whole thing into one single architecture. Input image, ResNet, feature map, tokenization, context vector through transformer encoder. Context vectors are going into transformer decoder along with object queries. Queries are refined here, and then those queries are passed through 2 MLPs, one for class and one for box, to finally predict the class and box. So overall, it looks very simple, but we are still left with a bunch of questions. So these are the questions. How is the loss function constructed? What exactly are the query key and value in this case? What exactly is the object query? Is there position embedding? Where is that? How is that added? What exactly does our MLP or feed-forward neural network look like? We did not zoom into the encoder and decoder. How do these two things look like? What happens to this? I think we discussed a little bit. What happens to the output dimension after CNN? So output dimension after CNN will be number of channels, but those number of channels are then projected into embedding dimensionality. So this briefly we have discussed, but we have to go through all of these. Now, there are a few different things which I want to discuss before we go into this, which is very interesting. Okay. Let me decide. Actually, let me show you the architecture first, and then we can go through the loss function. So this is the encoder part. So CNN part is very easy. I don't think I need to spend too much time on this. This is the encoder part. So transformer encoder, the whole transformer encoder is consisting of bunch of transformer encoder blocks. So what is the input into the transformer encoder block? The starting input is the tokenized sequence, which is obtained from the feature map. Now, inside each transformer encoder, so this is one transformer encoder block, so there will be n number of blocks. Okay, so I'm zooming in on one of them. You know already what is this? Layer normalization followed by multi-head self-attention. This is the residual connection, then followed by layer normalization, multi-layer perceptron with residual connection. So this is basically one transformer encoder block. Like this, there are few transformer encoder blocks in series inside the entire transformer encoder. So now what comes out of this, you know that after each transformer encoder block, you will have a transformed token sequence, right? The context vector will become richer and richer and richer. So by the time your sequence of context vectors reach here, you will have a very rich set of context vectors. Now, one thing we can try to understand here is where exactly is the position embedding coming? So that is what I'm going to show you now. Don't get intimidated by this picture. I will exactly talk about what this is. I think we had briefly mentioned in the transformer part, this was few lectures ago, that the position embedding that is used in the original transformer paper was something called as sinusoidal position embedding. Sinusoidal position embedding meaning it's not necessarily a learnable position embedding. It is a position embedding based on a sine formula. So I can just show you the formula. Sinusoidal position embedding. So the position embedding was created using a formula that looks like this in the transformer block. So, and the values of those position embeddings, which are unique, can be plotted on a graph like this. Basically, it's not a learnable position embedding. It's a fixed position embedding. So here also, the authors used sinusoidal position embedding when we are looking at this sequence of tokens. Okay, so these sequence of tokens, first of all, we have to convert those tokens into query, key, and value. So sinusoidal position embedding is added before converting it to query and before converting the token to key, but for value, it's not added. So just look at this diagram. So you have sinusoidal position embedding value, and what will this value depend on? It will depend on the spatial position. So this spatial position is 0, 0, this is 0, 1, this is 0, 2. So you can construct two sine functions, one sine function to take care of x coordinate, one sine function to take care of y coordinate. And I think you can concatenate those two to create a sinusoidal position embedding whose dimensionality. So what should be the dimensionality of this added position embedding? It should be whatever is the dimensionality of your embedding, input embedding. So if the D model is 768, your sinusoidal position embedding should also be 768 dimensional vector. Otherwise, you can't add it. Now, this position embedding is added in query and key, okay? And then this query, key, and value is what is going into your multi-head self-attention. Now, one important thing to notice here is in the architectures that we have discussed so far in this course, the position embedding was injected only once, right? It's only injected at the starting. Or sometimes in Swin Transformer, it was injected inside the formula. Like if you remember relative position bias, it was like softmax of query key transpose by square root of D plus there was a position embedding Bij term. Qi Kj plus mask Ij. So here position embedding was added after converting the tokens to query and key, and this was the relative position embedding. This was in Swin Transformer. But usually in most of the other transformers that we have discussed in this course, position embedding is added before query key transformation, just like here also. But it's only done once usually. But here in detection transformer, what the authors did is they injected the position embedding not just before the very first transformer encoder block. They injected it in the second transformer encoder block. They injected it here, here, and in all the transformer encoder blocks. Usually it is done only once, like at the starting. So this is one difference. So let me just try to understand. Yeah, in general position embedding. So here what is done is it was done corresponding to every multi-head attention. In general, position embedding is added over here. The tokens, you will have tokens, and then to the tokens, position embedding will be added. I think the reason why position embedding is injected in all the transformer encoder block is maybe to make sure that the model remembers the spatial information throughout the transformer encoder block series. I think that's the qualitative reason, excuse me. What is the intuition of not adding it to V? Because attention, so position embedding is primarily needed for calculating attention, nothing else. And attention is calculated using dot product of query and key, attention scores and attention weights. So that is why position embedding is needed only for query and key. Okay, so this is what is the only thing I would say which you might find different from all the other transformer encoder blocks that we have discussed so far. So the position embedding part of the transformer encoder, that's it. Now let's look at the decoder. Decoder is a little bit more complicated. So here, please pay good attention. So into the decoder, as we discussed, so this time I'm flipping the decoder from top to bottom to top. So previously input part of the decoder was here, output part was here. Here, just for the convenience of drawing, just consider that the flow is from bottom to top, okay, like this. It's just for my personal convenience of drawing, nothing conceptually different. So decoder has just like, now let me show you this diagram. Just look at this diagram. Decoder has, first of all, a multi-head, mass multi-head attention here, another multi-head attention here. In encoder, you had only one multi-head attention repeated n times in series. I mean, one multi-head attention in the transformer encoder, but then that transformer encoder block was getting repeated n number of times. Here, the transformer decoder block has two multi-head attentions before the multi-layer perceptron. So this is MLP, this is multi-head attention, this is multi-head attention, but these two multi-head attentions have there is a difference. So that is what we are going to discuss now. And hopefully at the end of this lecture, you will also understand this figure in a better way, right? So let's spend some time on the decoder. So in decoder, we have object queries. We also have outputs, which are context vectors coming from the transformer encoder. So now two interactions should happen. First is these queries themselves should interact to create an attention. These set of context vectors, they already went through transformer encoder, which means they already have, the global attention already has been baked into the context vector. Do you understand what I mean by that? The context vectors are created from image feature token. I mean, features converted to tokens. They were already passed through a bunch of transformer encoders in the transformer encoder part, in the transformer encoder block, which means global self-attention is already baked into this. So if this token and this token should pay very high attention to each other, it's already taken care of because these context vectors are already having that information. But queries are now initialized randomly, right? Which means this query, how do you know this query, the context vector corresponding to this query and this query should have high attention, or not context vector, this token corresponding to query number 1 and query number 4. How do we know how much attention they have to pay? So somehow some attention has to be constructed, self-attention has to be constructed between queries themselves to make the queries enriched in the context. That is first thing. Second thing is, now queries should interact. These are object queries. These object queries should now interact with the incoming context vectors from the transformer encoder output. So some kind of attention has to be constructed between the object queries and the transformer encoder output. So this has two different names. So when you are constructing attention between query with itself, when I say query, please don't imagine this cube. That is not what I'm saying. Here, when I say query, I mean object query. So these are called object queries, which you can simply imagine as bunch of vectors initialized as zeros. So object queries, first of all, should be enriched into better context vectors by having self-attention within itself among those object query tokens. So for that, you have a self-attention module for after a layer normalization. So this is one transformer decoder block. So you have layer normalization followed by self-attention, and you have a residual connection here. So by the time it reaches here, by the time these object queries reach here, they would have get converted into better context vectors. But there is one detail which I want to note here. This diagram is completely ugly, which is why I'm going to start with a brand new diagram with no annotations. So object queries, these are object queries. They need to attend to each other, which means they should be converted to query key values. So object queries will be converted to query, to key, to value using WQ, WK, and WV. So this is self-attention where object queries are attending to themselves. Here it is written cross-attention, but I'll come to that in a moment. But here position embedding need to be added. So the kind of position embedding that is should not the object query start from the of course. So these lines that I'm drawing, okay, this line I'm drawing is not representative of the I just see if I draw this object query over here, my diagram will look like a bit confusing. So okay, I understand where the confusion is coming from. The only reason why I'm drawing it like this is to show that finally these after layer normalization are converted to query key values, right? So actually the way this goes is these three things will pass through layer normalization. Okay. And then it will get converted to query key value. So ideally I should draw something like this: query, key, and value. Okay. So I'm just drawing it as a shortcut here, but imagine that layer normalization has already happened. Okay. So please don't get confused. The count of object queries are number of objects you want to detect, like 100. Yes, correct. That's correct. Count of object queries should be same as maximum objects you want to detect in your image, or maximum objects you are expecting in your image. Okay, so now object queries should be added with the position information, because these queries are, this is query number 1, query number 2, 3, 4, etc. But here, these queries, there is no special position information that you know already, which means you can't use sinusoidal position embedding, because what is the meaning of the position number 1, 4, etc. here? There is no meaning. So you let the position embedding for these queries be learnable position embedding. So that is what is drawn. I have drawn in this figure. So you have learnable position embedding, which are added to the input token before getting converted into query, and before it getting converted into key, of course, through layer normalization. So I'm conveniently not drawing it by drawing a convoluted line here, but assume that layer normalization is done. Position embedding will be added before layer normalization. So, excuse me. So learnable position embedding will be added to query and key. Corresponding to object queries. Now, object queries will form self-attention inside the multi-head self-attention block to have enriched context vectors corresponding to object queries. Now, is that enough? It is not enough, because we need we need object queries to interact with the context vectors that are coming from the output of the transformer encoder. So now that we can draw here. So now what should happen? These object queries will go here. Now these are now outputs coming from the transformer encoder. They will also be converted to query key values. So now query key and value, and they should have a position embedding. Actually, let me erase one thing. There is one mistake in my drawing. They will not be converted to query key value. They will only be converted to key and value. Value and key. And queries will be the tokens, object queries converted into queue. So that is why this is called cross attention. So now look at this. The object queries will be converted using a WQ matrix into Q. But for key and value, you take the context vectors, which are the output from the transformer encoder. So the reason why this is called cross attention is because the sequence which ended up creating this Q is different from the sequence which ended up creating this K. The K is the result of the sequence which is from the CNN features. So CNN features were converted into token sequence. Token sequence became enriched context vectors from the transformer encoder. And now those are converted into or projected into key space. But for query, so usually in self-attention, query and key are in the same dimensional space, but they are projections of the same input tokens, same sequence of input tokens. So here, query is on the other hand in this cross attention, query is coming from the object query tokens. So they are projected into the query space. Key and value are corresponding to the these context vectors. And then you construct the cross attention. There are some questions. Okay, let me see. Wouldn't it make sense to take the object query which passes through the first transformer decoder block for doing the cross attention? Yes, that is correct. So you mean to ask, Shubhankar, shouldn't we take the enriched, shouldn't I draw it somewhat like this? Or rather something that passes through layer normalization? Shouldn't we take object queries which are from the context vectors, right? That is correct. So the only reason why I'm drawing it like this is to show that in the cross attention, at the end of the day, the origin of the query is not from the image, it is from the object queries. The origin of the key and value is not from the object query. The origin of the key and value is from the image, right? Then we are already getting enriched context vector of all queries from self-attention and then layer normalization. That will also go as input. That will also go as input to context. We are already getting enriched context vector of queries from self-attention and then layer normalization. Yes. So I'm so sorry for drawing like this, because if I don't draw it like this, the point that I want to make you understand is the origin of the key. The reason why this is called as a cross attention is because the origin of the query is not the same as origin of the key. Key and value here in this case originates from the image ultimately. Query here does not originate from the image. Query originates from the randomly starting, zero initialized object queries, right? On the other hand, here in the transformer encoder, query originated from the image, key originated from the image, value also originated from the image. So this is not a cross attention, this is self-attention. Because when you take dot product between query and key, the same sequence of tokens are now projected into the query and key space. Of course, it is after layer normalization, but I drew it like that to show you the origin. Where is it coming from? But here in this diagram, let me move to this. In self-attention, the origin of the query is from the object queries. Origin of the key is from the object queries. Origin of the value is also from the object queries. Are those object queries passed through layer normalization before coming to self-attention? Of course, yes. Then is there residual added after this? Yes. Is there layer normalization after this? Yes. So by the time your object queries reach here, so you have 4 object queries. Let me just draw 4 of them here. So you will have 4 here. You will have enriched context vectors. right? So now these are 4 enriched context vectors due to the self-attention, where now queries are paying attention, these object queries are paying attention to each other in these 4 context vectors. Now these context vectors are converted into queries. So the origin of the query, which is there in this cross attention, is ultimately these object queries. Similarly, origin of the keys and values is the image, but where is the key and value calculated from? It is calculated from the context vector which came out of the transformer encoder block. So the reason why this is called cross attention is because when you take q dot k transpose, q is coming from a different sequence and k is coming from a different sequence. Where is q coming from? Q is coming from the context vectors corresponding to object queries. K is coming from the context vectors corresponding to the image feature tokens. All right. And now let's look at this image once again. So now hopefully you will understand this slightly better than what you knew before. So look at this. So here you are having, so this is the decoder and right side is the encoder. So in the encoder, you have input token embedding and those token embeddings pay attention to each other in this self-attention. And then finally, they are converted to context vectors here. So this is MLP, this guy, and this is the MSA, multi-head self-attention. Now, this is converted to value and key, but query is now coming from here, from the decoder input. So this is the query, and this is sort of like cross attention, and then query.key, softmax of this multiplied by value, followed by multi-layer perceptron, and then softmax finally for predicting the next word probability. So almost exactly this is what is happening, except the positional embedding. So here, position embedding is only added once. The sinusoidal position embedding is only added once here. But in our case, they added it at every, in the encoder, they added it at every transformer encoder block over here. This was sinusoidal position embedding. And here, yeah, I did not mention the position embedding added here. So in object queries, there is no inherent position information. So you are adding learnable position embedding. So plus learnable position embedding, LPE. There is no such term existing. I just made it up, but LPE, learnable position embedding, is added to query and key. Value, it's not added. For cross attention, can you tell me, are we going to add the same position embedding to Q and K in cross attention? For Q, we will add LPE or sinusoidal. Learnable position embedding. Learnable position embedding simply means you randomly initialize a position embedding vector, and through backpropagation during the training, the values of that position embedding vector will get modified. In sinusoidal position embedding, it's like a fixed position embedding vector. It's not learnable. And here, sinusoidal is added. Why is sinusoidal added here? Because this key is coming from your image sequence, which inherently had a spatial 2-dimensional structure. So there we don't add learnable position embedding. Do we need to add any kind of position embedding to the encoder output? Encoder output meaning, you mean here, right? I mean, essentially, this is the encoder output. Encoder output is converted into key and value. Yes. So encoder, the key that is resulting from the encoder output is added with the sinusoidal position embedding. Now, instead of showing my handwritten ugly diagram, let me show you a slightly cleaner diagram. Okay, so just don't get afraid. Let's go through this one by one. You have object queries, and object queries should pay attention to each other. So for the self attention, the origin of these object queries are origin of the query and key value vectors are the object queries themselves. And there, for query and key, we add position embedding, and all of this happens before layer normalization. Okay. So why do we add learnable position embedding for object queries? Because we don't know what is the spatial relationship between object query, anything. We don't know anything about object queries spatial relationship. They are literally 4 or 100 or 50, how many ever objects you want to predict. So object queries are you don't know what are the relationship between them. So it's even, in my opinion, not correct to call it as position embedding. Just call it as some learnable embedding. Whether it is learning position or something else, you don't know. But in usual literature, people find it easier to call it as position embedding. So that is added to query and key. Then not added to query and key, those are added to inputs before getting converted to query and key. Now in cross attention, query comes from object queries. So see this, query comes from object query, that is the origin. But in the cross attention key and value, its origin is from the context, this transformer encoder output, which is resulting from the image. But are these three things coming directly from here, or are they coming from layer normalization, self-attention, etc.? So this query is created using the context vectors resulting from layer normalization, self-attention, residual, etc. And then another layer normalization. So at only this point, you have 4 context vectors corresponding to these 4 object queries. Those 4 context vectors will be converted to 4 key vectors in the key space. This, no, sorry, not 4 key vectors, 4 query vectors in the query key value space. In the same query key value space, you will need key and value, so that you can take dot product between query and key. And this key is originating from your context vector corresponding to encoder output. Value is also originating from the same. However, please note that since the query is coming from your object queries, the position embedding here that is added is learnable position embedding. Since key is originating from the image where the position information is kind of known, you add sinusoidal position embedding. Okay, slightly complicated, but I think you will understand if you spend a bit more time. Context vector will directly goes to the cross attention head, or will it go via decoder block? It will be taken to the cross attention directly after projecting. Okay, tokens should be projected to query key value space, but it will go to the cross attention, just like this, as you can see here. So here they are not passing through here, right? Here they are directly going into the multi-head attention. Same. Okay, so now what is there? Okay, now there is a very important thing which I want to discuss. So after all of this, when we make a prediction, this is what we want, right? Let's say I have 2 objects to predict in my image. If my image is like this, and if I had a person and a cat, okay, I only want to predict 2 bounding boxes in this case. But let's say I have 4 object queries. 4 object queries that look like this. But I have only 2 ground truth bounding boxes. So prediction, bounding box, B box. Now my question is, you want to match only one unique prediction to one bounding box. Because that's the whole point. That's the whole value proposition of detection transformer. There is no need for non-maximum suppression, because you are not going to predict duplicate boxes corresponding to the same ground truth. This is ground truth, bounding box corresponding to ground truth. So either you will say this prediction corresponds to this one, this corresponds to this one, and this correspond to no object or background, or let's say no object phi. Or you will say this corresponds to this corresponds to this, and this are corresponding to null objects. So what you do is, if you have 4 object queries, and in the ground truth, if you have only 2 boxes, you add 3 null objects, 5, 5, 5. So 3 null objects. So you have 2 ground truth objects and 3 null objects. Sorry, not 3, 2 null objects. Guys, just give me a second. There is a little bit of sound coming from outside. Just give me 1 second. Sorry about that. So what is done is, if you are having ground truth boxes, guys, just a second. Sorry about that. There is some drilling operation going on. I just had to ask them to pause for a bit. All right. So what we want to do is 4 predictions should be matched to 4 ground truth boxes, or 2 ground truth boxes and 2 null predictions, so that every object query is corresponding to one unique ground truth, right? So this is what we want to do. So basically, it's like a matching problem. So you predicted a set of boxes, and those predicted set of boxes now should be matched to some good ground truth boxes plus some some null objects. Now I'll show you what this means in in a bit better way. But the question is, how is this matching usually done? So in non-maximum suppression, how was the matching done to ground truth? If you wanted to construct the loss function, you will have finally a predicted bounding box. You will have a ground truth bounding box. So this is, let's say, the final predicted bounding box emerged out of the non-maximum suppression. This is the actual ground truth bounding box. You can construct some sort of loss function using IOU. You can say the preciseness of your predicted box with respect to ground truth box can be calculated based on IOU. But here, something unique has to be done, because you have to match one box with one prediction. You don't have the ability to predict large number of boxes and eliminate those duplicate boxes and then say that these are your final predictions. You can't say that. So I will show you this with a simpler example that explains Hungarian loss. So Hungarian loss is basically a loss function that is defined in context like this, where you basically try to have a set that is mapped to a set of other objects. So this is the example. Let's say you have 4 workers and you have 4 jobs to be done. Now these workers will quote different amounts of pricing for different jobs. So worker number 1, so let's call them red, blue, green, and pink. So this worker will have 4 jobs, and worker number 1 is quoting $1, $2, $3, and $4 to the job. Worker number 2 is quoting like this. Now let's say you are the person who is the contractor, and you have to assign a unique job to one worker such that your total cost is minimized. So you want to get job 1, 2, 3, 4 done. 4 jobs you have to get done. And to get those 4 jobs done in the most cost efficient way, you have to find which worker needs to be assigned to which job, right? So that is the problem that we are trying to solve. Now here it kind of looks easy to figure out the optimum, because it's an optimization problem. In the case of the bounding box matching, like which object query corresponds to which bounding box, also same thing applies, because you will have 2 ground truths and 2 null objects. So totally there are 4 objects. And then there are also 4 boxes that are being predicted, because you have 4 object queries. Now you have to match whether object query 1 corresponds to ground truth 1, ground truth 2, or 5, which is the null object. And you have to do it in such a way that the overall loss of the model is minimized. So here, there is a very nice trick or very nice sequence of steps that is done, that is called as Hungarian matching. So this name Hungarian came from the fact that the scientist who proposed, I completely forgot his name, he named it after 2 Hungarian scientists who were working on a similar problem. So the original algorithm from which this Hungarian matching came was called Hungarian algorithm. And the scientist whose name I unfortunately forgot, he named it after 2 Hungarian scientists who kind of laid the groundwork for this algorithm. So the algorithm is as follows. So first you create this, cost matrix. So this cost matrix is 4 jobs, 4 people. You have to find the unique job person pair so that all jobs are getting done. You can only assign one job to one person. So first is you subtract a minimum number from every single row. So every row, for every row, find what is the minimum number and subtract it. So for example, in row number 1, the minimum number is 1. So you subtract 1 from row number 1. So what does that mean? That means the red worker is reducing his cost, which is proposed for every single job, by $1. That's the meaning of that, right? Similarly, and now please tell me, if I reduce the cost of every single job, let's say my optimum job distribution that I as a contractor was, I gave job number 1 to this guy, job number 2 to this guy, job 3 to maybe this guy, and job 4 to this guy and job 3 to this guy. Let's say this is what I did as a contractor. Okay. Let's say I'm not saying this is the optimum distribution. I'm just saying if this was the optimum distribution, and let's say suddenly this guy reduced his quotation for all the jobs by $1. For job 1, he reduced the pricing from 1 to 0. Job 2 became 1. Job 3 became 2 and job 4 became 3. Does it change the optimal distribution? It doesn't change the optimal distribution. You can think of it logically. No need to think about it mathematically, because let's say it changed the optimal distribution, meaning because this guy has now changed the pricing of job 1, he can be assigned some other job. The benefit that this contractor is getting is not changing, because the contractor already got the benefit. The -1, the benefit of reduction of the $1, the contractor is already getting, irrespective of whether this person was given job 1, 2, 3, or 4, because he reduced the pricing of all the jobs by $1. So that benefit is already baked in the current distribution itself. So if the current distribution was the optimal job distribution, that is not going to change because of the fact that this guy has reduced the pricing of all the jobs by $1. So by the same logic, I can then subtract any number from each of these rows. So from the row number 1, I can subtract any number. Row number 2, I can subtract any number. The number has to be constant throughout the row. As long as I do that, there is no issue of my optimal distribution changing. So now let's find out the minimum number from each of the rows. So the minimum number in this row is 1. So I subtracted 1 from the row. So the numbers became like this. Minimum number in the row number 2 is 1. So the second row became like this. For row number 3, again, minimum number was 1. So it became like this. Same for row number 4. So now you see, one good thing that has happened is, you see the cost. Now, when you see 0 cost, it's easy to find the minima, because here you can see that for job 1, there is somebody offering 0 cost. For job 2, there is somebody offering 0 cost. It would have been very easy for us to find the minima if, for example, this was also 0. Because then all we need to look at is, for job 1, is somebody giving me 0 cost? Yes, this guy. Is job 2 somebody giving me 0 cost? Yes, this. Is job 3 somebody giving me 0? Maybe if this was 0, I could pick that. And same for job 4. Excuse me a second. So this is called as zero cost assignment. So if we can somehow convert the minimum cost of jobs to 0, we can easily pick the minimum total cost assignment. Because now if I assign job 1 to this guy, job 2 to this guy, job 3 to this guy, and job 4 to this guy, my total cost is 0 plus 0 plus 0 plus 0. Its total cost is 0. All the other numbers are positive numbers, which means I cannot go below 0. There is no negative cost. So if I can somehow come up with 0 as numbers in every row, then I can somehow easily figure out an optimal distribution. So now by the same logic which we applied here, I can also apply the same logic to column. If the pricing of job 1, let's say every worker number 1, 2, 3, 4, everybody reduced their pricing for job number 1 by $1. Does it affect the optimal distribution? It doesn't, because the market is not changing. The job 1 overall, all it means is to get the job 1 done, the contractor needs to pay $1 less, irrespective of which person this contractor picks. So now what we can do is we can subtract the minimum number from every column also, just like how we did for every row. You will soon understand why we are doing this step in the context of detection transformer. So this was what resulted after subtracting the minimum number from each row. Now from each column, for every column, first to third column, the minimum number is 0. So there is nothing to subtract. For the last column, minimum number is 1. So you can subtract 1 from all these numbers. So last column will now become something like this. So you subtracted minimum from rows, minimum from columns. So now this is your current cost, distribution matrix. Now what you do is you find this sounds a little bit like some geometric technique, but this is exactly how you can implement the Hungarian matching algorithm. Now you draw some lines, minimum number of lines, which will cut through every single zeros which you have in the table. So I can draw one line like this, another like this, and another like this. Now I drew 3 lines, and 3 lines are cutting all the 4 zeros, right? So I mean all the zeros in my table. So the number of lines, let's say, let us call it as M, is 3. But number of workers that I have to assign is 4. So let me show you this. So find the minimum number of lines that cross out all zeros in the table. So the minimum number of lines that are required to cross out all zeros are 3. But I have 4 people to assign jobs to. So now we have to repeat one more step, which is now look at from the remaining numbers which are uncrossed. What is the minimum number? The minimum number is 1. Now, if I were to subtract 1 from all these rows, the problem is some of these numbers will become -1. I don't want negative cost. I want the minimum cost to remain as 0. So what you can do is, first, you can add this 1, this minimum number, to all these crossed rows and columns. So I can add 1 here. So add +1, +1, +1, +1. So since I am adding same number to the column, my optimum assignment will not change. Here also add +1. If minimum is 2, you add +2. And then here also you add +1, +1, +1, and +1. So now what happened is you have 1 added to these 3 cells, 1 added to these 3 cells, 1 added to these 2, and 2 is added to these 2 because row-wise, I mean column-wise +1 was added, row-wise also +1 was added. So here 2 is essentially added for these 2. Now what you can do is, now you can subtract this minimum number 1 from every single rows. So now if this 1 is subtracted, +1 and -1 will cancel each other, +1 and -1 will cancel each other. This 2 will become 2 minus 1, which is 1. This 2 will, again, -1 is added here. So 2 minus 1 is 1. So finally, your matrix will look like something like this. So here there is a mistake. Here there is 1. So your matrix will look something like, yeah, okay, it's 1 only. So matrix will look something like 1, 7, 4, 3, 2, 1, 1, 1. So what we have done is we have eliminated, not this. We have eliminated, this 1 also. So you wanted to subtract this 1 without introducing negative number. So to not introduce negative number, you add this 1 to this crossed out rows and columns, and whichever cells are getting double crossed by 2 lines, their value will increase by 1. For the rest of the cells, their value will not change because you are also subtracting this 1 later from every single rows. So at the end of the day, I know that I have told you too many number of steps, but if you zoom out and look at it, it's a little bit simple. At the end of the day, you will get something like this. You will see that every row has some 0 in it. So this row has a 0. So you can say a red person can be assigned job 1. Blue person can be assigned job 2. Green person can be assigned job 4 because this person is quoting. The green person cannot be assigned job 2. Why? Because job 2 is already assigned to blue person. What's wrong with green person assigning job 2? Because then blue person cannot take job 2. Blue person will have to be assigned maybe job 3. But then cost increased. by 1. So, and then green person can be assigned job 4, and this pink person cannot be assigned job 2 or job 4 because those two jobs are already taken, but the pink person can be assigned job 3. So now the total cost of doing this job is 0 in this zero cost assignment, 0 plus 0 plus 0 plus 0. But to know the actual total cost, you bring back your original matrix. So your original matrix was this. So let me copy paste it here. So your actual total cost will be corresponding to this 0, it was originally 1. So 1 plus corresponding to this 0, it was 1. 1 plus 1 plus 1 plus 3, which is 3 plus 3, 6. So this will be now the 6 is the now the minimum cost. 6 is now the cost that you can, go to, like in the minimum case. And to achieve the least cost of 6, you have to assign this red worker to job 1, blue worker to job 2, green worker to pink job 4, and pink worker to job 3. If you do that kind of an assignment, you will achieve minimum cost, which is 6. Now, why are we talking about this jobs and person matching and all? Because same thing is what is happening in our case, because we have a bunch of bounding rectangles that are predicted through our object queries, and we want to match them to a certain bounding rectangle because we don't know which predicted object query is which bounding rectangle. We have to come up with some parameter, right? So first what we do is we say that if I have two predicted bounding boxes, okay, this is, let's say, predicted bounding box 1 and this predicted bounding box 2 in the image. And let's say in the image, I have two ground truth bounding boxes, ground truth bounding box 1 and ground truth bounding box 2. Now, what I want to do is I want to minimize my cost by assigning this person one of these two jobs and this person one of these two jobs. So now you can think of the predicted boxes as people, the ground truth boxes as jobs. And I want to assign the correct bounding box to the correct ground truth so that my total loss is minimized. And to find the matching, you have to use some sort of Hungarian matching. Now the question is, here you were already given the cost. You already knew what was the cost. Here, what is the cost? So if these P1 and P2 are people, what is their cost? What is the cost of P1 for being assigned to ground truth 1? What is the cost of P1 being assigned to ground truth 2? What is the cost of P2 for being assigned to ground truth 1? And what is the cost of P2 for being assigned to ground truth 2? So we need to construct some sort of mathematical cost function. And then we have, yes, IOU is one. I mean, good example. IOU is not the only one, but I'll come to that. So first we have to construct some sort of cost for assigning prediction number 1 to ground truth 1 or prediction 1 to ground truth 2 individually. You also have to know the cost associated with assigning prediction number 2 to ground truth 1 or ground truth 2. And then once we have the cost matrix using Hungarian matching algorithm, we can figure out the optimal matching between all the predicted boxes and all the ground truth boxes. So this is what, can the number of ground truth boxes be more than the number of predicted? No, it can't happen, because that's why I said the object queries, number of objects queries is assigned to be a big number like 100, so that never the number of ground truth boxes will be greater than the number of predicted boxes. So that's the reason why here we took an example of 4 object queries, but in actual detection transformer paper, they use 100 object queries or something. Now, there is one more question here. When do you not need Hungarian matching? Let's say I have only one ground truth, and let's say I have 5 queries, 5 object queries. Do I even need Hungarian matching? No, I can simply take some IOU or something, right? If I just have one ground truth, and if I have multiple queries, if I want to find which query fits the ground truth the best, minimizing the cost, I don't need matching. I simply have to calculate the cost and find whichever has the lowest cost. But now let's say, when do you actually need Hungarian matching? Let's say I have 2 ground truth and 5 predicted boxes. What will happen is, so this is an example which I just wrote to make you understand in the context of detection transformer. So let's say now I am considering the prediction number 3. Okay, and I'm comparing that with, so I have 5 predictions and 2 ground truth. And now compare the prediction number 3 with ground truth 1, prediction number 3 with ground truth 2. And let's say I was just looking at IOU to perform the matching. What may happen is if I'm just looking at IOU, if I have ground truth 1 and ground truth 2, let's say these are my ground truth rectangles. And my 5 predicted boxes are like this. One box is, this is P1, this is P2, then this is P3, then this is P4, and this is P5. Okay, so these two are the ground truth. Now, if I'm only thinking about IOU, the problem is the IOU between G1 and P3 is greater than 0. The IOU between G2 and P3 is greater than 0. But IOU between G1 and P5 is 0, G1 and P4 is 0, G1 and P2 is 0, G2 and P5 is 0, G2 and P4 is 0. So now if I'm only looking at IOU, I will end up saying that this P3 box is the box that predicts both ground truth 1 and ground truth 2. But that's like predicting same box for 2 objects, which is not what we want. And this is happening because if we don't rely on Hungarian matching, and if we only look at IOU, and if we only look at the maximum value of IOU, we might end up predicting same box for 2 different ground truths. It may also happen that we may predict like not so great boxes. So here is one more problem. Let me show you something like, let's say, yeah. So one more problem is the IOU between ground truth 1 and P1 is 0 because there is 0 overlap between them. IOU between ground truth 1 and P4 is also 0 because there is 0 overlap between them too. But you can see that P4 is a very bad box if it were to be matched with G1 because P4 is so far away from ground truth 1. But P1 is kind of closer to ground truth 1. But if we are simply considering normal IOU, its IOU score is 0. Intersection over union for P1 and ground truth 1 is 0. P4 and ground truth 1 is 0. So we are not able to distinguish these boxes. So Hungarian matching is first done so that we can assign correct predicted boxes to corresponding ground truth boxes. And then we can calculate the loss, total loss. So now let's see how the total loss is calculated. So this is the detection transformer loss. Okay, so there are 2 losses. One is broadly, one is classification loss, second is localization loss. Classification loss comes from the fact that the model may draw a good bounding box, but model may say inside the bounding box, you have a cat instead of a dog. But that might be a wrong prediction. So for making mistakes in classification, in assigning the class, you have to penalize the model. Also, to kind of penalize the model for drawing the bounding box at the wrong location, you should have some loss. So that loss is based on 2. One is L1 loss and another is called global generalized IOU loss. So I'll come to this generalized IOU loss in a moment. But this is where I think somebody had mentioned about IOU loss in the context of what should be the loss function. Yes, IOU is coming into the picture, but in a slightly modified way. And L1 loss is simply this. You have 4 parameters that are getting predicted, X, Y, W, H. So L1 loss is simply X predicted minus X ground truth plus Y predicted minus Y ground truth plus W predicted minus W ground truth plus H predicted minus H ground truth. So this is sort of like L1 loss. So this is penalizing the model for making mistakes in the position of the rectangle. This is penalizing the model for something very interesting. I'll come to that in a moment. Classification loss is penalizing the model for saying that inside this bounding box, whose coordinates are x, y, x prime, y prime, w prime, and z, h prime, it is a cat instead of a dog. So yeah, I'll come to where is Hungarian loss here. So now let's look at this. Hungarian loss is coming in the fact that, first of all, how do you compare the prediction and ground truth? So here we are, when we are saying classification loss or when we are saying localization loss, We are comparing between predicted box for ith object and ground truth box for ith object. Now, how do I know which among the predicted box is the box corresponding to ith ground truth object? So to match, so if we are predicting 5 boxes in the prediction, and if there are 5 ground truths, first I have to match them. So for that matching, you have to use Hungarian matching. And once you have matched prediction ground truth pairs, and that for that, first of all, you have to calculate the cost of every pair, right? So you have to, if you have 5 rectangles here, actually you had 5 workers and 4 workers and four jobs. And you calculated the cost for every single worker for every single job. Similarly, this detection transformer loss, you have to calculate between every single predicted box and every single ground truth box, right? So you will have, just like how you have the quotation from every single worker for every single job, you will know what is the total detection transformer loss, considering 3 losses, the classification loss and the 2 parts of the localization loss, which is L1 loss and global IOU loss. You will know for predicted rectangle number 1 corresponding to ground truth 1, what is the total detection transformer loss? For predicting rectangle number 1 corresponding to ground truth 2, what is the total detection transformer loss? Like that, I will have, if I have 5 boxes to be predicted, which is predicted, and 5 boxes in the ground truth, I have 5 by 5, 25 total losses. Now, before calculating the total loss, I have to know which box made the correct prediction, like which box should be assigned to which ground truth. For that, you use Hungarian matching. So now this term, I hope you understand. Classification loss is simply if the class was predicted in the wrong way, you can take a softmax cross entropy loss. Localization loss has L1 and global IOU term. L1 is the most straightforward loss. Global IOU, let me show you. And then finally, the total cost is not simple addition of these 3 losses. So this is the loss due to classification. This is the L1 loss. This is the global IOU loss, which I am about to explain. This is the total localization loss. And they are added by weighting with these lambda values. So lambda values, the paper uses certain specific lambda values, but of course, we can try it as we can try different values as hyperparameters. Now, what is this IOU? The problem with or global generalized IOU, the problem with normal IOU is this. Let's think about these 2 cases, okay? Case 1 and case 2. IOU is 0, but we know that if this was ground truth and if this was the corresponding prediction, we know that case 1 is better than case 2, right? So just by taking IOU, we are not able to get a good representation of the fact that case 1 is significantly better than case 2. Then what can we do? What can we do is we can slightly modify the formula where generalized IOU is the actual normal IOU minus some extra term. Now, what is this extra term? It has something called as area of C. Now, C is area of this smallest rectangle enclosing both ground truth and predicted boxes. So now C is greater in case 2 than in case 1. Now look at this formula. Generalized IOU is IOU minus area of C minus area of P union G. P is prediction, G is ground truth, divided by area of C. If I simplify the formula, it will become IOU minus 1 plus P union G by C, because this, if you take minus with area of C divided by area of C, that will be minus 1. Then this minus and this minus will become plus 1. So plus P union G by C, okay? So anyway, IOU between ground truth and prediction is 0 in both of these cases. So let's say IOU is 0. So then this formula will become generalized IOU equal to minus 1 for this special case. I'm showing this formula for this specific case. Generalized IOU equal to minus 1 plus P union G by C. And now let's say the area of P and G was the same, right? So now we can say if they are the same, I can say P union G equal to 2P or 2G, right? By either of these I can call. So now generalized IOU will be minus 1 plus 2P divided by C. Now look at this formula. In which case is C greater, case 1 or case 2? C of 1 and C of 2. In which case is C greater? In case 2 is C greater. So C of 2 is greater, which means in the generalized IOU score will be bigger if the C value is smaller, right? And C value is smaller in case 1, which means generalized IOU score is higher for case 1. So essentially, generalized IOU is a better score to consider if you want to take into the fact that there might be rectangles that are initially far away, but you don't want to penalize two rectangles in the same way just because they don't have any overlap. So this is a better distance formula between the rectangles. So these are the three loss terms that are part of the detection transformer loss for calculating the loss between any two pairs of rectangles, any predicted rectangle and any ground truth rectangle. Then which pairs are finally considered? The pairs that are finally considered is based on the Hungarian matching. Now, okay, that is good. I just wanted to show one more thing, just one more detail, which I don't think I have mentioned. So I talked about the FFN, feed forward neural network. So forget about this. Let me put a rectangle here. So just forget about that. This feed forward neural, these are now the context vectors corresponding to object queries. Okay, these 1, 2, 3, 4, 5, 6. Now these context vectors are responsible for predicting the class and the box. Now, how do we predict that? These object queries are simultaneously passed through two feed forward neural network. One is for multi-layer perceptron for class. One is multi-layer perceptron for box. So this MLP will predict whether the item inside our box is whatever object is person or dog or cat or whatever. MLP will predict, and here it will be basically a softmax probability score like 0.9. So if there are only 3 objects in the training data, it will look like 0.9, 0.05, 0.05. Right? So then this itself can be directly used as the confidence score. Then box MLP will tell you what are the 4 coordinates of the box: h, w, x, y, w, h. And one interesting detail which I want to note, which is not a big deal, which even if you don't know, it's okay, is that just that during the training of detection transformer, they calculate the total loss by constructing the loss using every single decoder layer, not just the whole decoder output. So this layer will have a context vector output. This layer will have a context vector output. This layer will have a context vector output. Every single one of them will be a sequence of context vectors corresponding to your starting object queries. So using all those object queries from every single layer, every single transformer decoder layer, you can perform predictions. So each of those predictions will result in different loss. So those losses, so this loss is from this loss is from the transformer encoder layer number 1. This loss is from the transcoder encoder number and layer number 2, layer number 3, etc., and layer number n. And then you can sum up those losses to calculate the total loss. And then this total loss is used while doing the back propagation. This is, however, not done in inference. In inference, let me delete all of this. In inference, you only consider this one. You don't consider all these intermediate layer context vectors. You only consider the last one. So which means you don't have all these losses. You only have one loss, which is corresponding to the last context vector. Okay. Do we have output of 100 nodes in the class MLP? Yes, of course. Because when you say 100 nodes, you mean these 100 object queries, right? I hope that's what you mean. 100 object queries. Yes. So yes, if there are 100 object queries, you will have finally 100 predictions. And for those 100 predictions, you have to construct 100 losses. But how will you construct 100 loss if you have only 5 ground truth? If you have 5 ground truth, you will have 5 ground truth and 95 null objects. For null objects, there are no losses. For 5 ground truth, there will be loss. So that will be the total loss. And the total loss will be used for training. So now let's get back. I want to do one implementation, but let's zoom out and go through the architecture once more. So this is the architecture. Just to reiterate, image feature extraction through backbone CNN. The extracted features are converted to tokens in the embedding dimensional space, and that is passed through transformer encoder. Transformer encoder has a bunch of transformer encoder blocks, and those blocks will convert these sequences into context vectors. Then those context vectors are used in transformer decoder, but before that, you initialize the bunch of object queries, which are null vectors. Those object queries will pay attention to each other in a multi-head self-attention block. In that multi-head self-attention, object queries pay attention, and before that, position embedding is added. For object queries, the position embedding is, which one was it? Was it learnable embedding or was it sinusoidal for object queries? For object queries, it was learnable because object queries do not have any inherent position information. But the 2D feature map is 2D. There was an inherent position information, which means we could construct a sinusoidal function, which acts like something that increases along the row, something that increases along the column, etc. So for these context vectors, in every single transformer encoder, the sinusoidal position embedding was added. Now, this is in the transformer. Let me go through this diagram. So this is the transformer encoder decoder part where object queries are paying attention to each other. But then these object queries, once it passes through the self-attention, it should now pay attention to output from the transformer encoder, which are context vectors. Now, those context vectors are converted to query and key and value. Query is originating from the object queries. So this is called cross attention because the sequence that produce the query and sequence that produce the key and value are different. So this is called cross attention. But here, the position embedding corresponding to this object queries was learnable position embedding. Position embedding corresponding to the context vectors were sinusoidal position embedding. Okay, so that difference is there. And then cross attention converts these object queries into even better context vector. So now this context vector is rich in information, not just about whatever information it has to communicate between each other, but also about the information about the feature map, which came from the image. Now these context vectors can be converted into object bounding boxes and classes. And for that, we use feed-forward neural network, which has two MLPs, MLP for class and MLP for bounding box, B box. And if there are 4 object queries, there will be 4 boxes that are predicted. And for constructing the loss, we have to map these boxes into ground truth. If we have only 2 ground truth, and if there are 4 predictions for remaining 2 ones, because we need a square matrix for the Hungarian matching. So for the remaining 2 ground truth, we add null objects. So then we map, we construct the loss using detection transformer loss. For every prediction, we try to construct the loss with every ground truth. And there are 3 components for the loss. The first component was the object classification loss, which is due to making a wrong classification prediction. Second component was due to localization. Localization is subdivided into 2 parts. One is L1 loss. L1 loss is absolute losses between prediction and ground truth for the the bounding box center coordinates and the bounding box height and width. The global generalized IOU loss is a better version of IOU loss, which considers the distance between the predicted rectangles also. So using these 3, we can construct the detection transformer loss between every single prediction and ground truth. But then every single prediction and ground truth are not, one ground truth has 1 prediction. And how do you know which one is that? You use the Hungarian matching finally. So then you can use the final loss to perform the backpropagation. In training, for calculating the final loss, you're also considering predictions made by not just the last output of the transformer decoder, but also the in-between intermediate outputs. They are also taken to construct losses due to the first layer, second layer, third layer, etc. And then those losses are aggregated for the total loss. During inference, that is not done. Only the prediction taken from the last layer is considered. Okay. How many of the 100 object query tokens goes into class MLP into the box MLP? Every single one. Every single 100 object query context vectors corresponding to object query will go through the class MLP and box MLP. Because finally, if there are 100 queries, we need to make 100 predictions. What are the predictions? The class and the box. So if you have 100, the reason why you started with 100 query is to predict 100 boxes. Now, not all boxes will be having an object. A very low confidence boxes will be no object, null object. They will be mapped to null object from the ground truth. Now let's do one thing. Let's do a quick, not implementation, inference, because implementation will take very long time, but inference is very quick. So I'll first share the code with you. This is very, very easy. Okay, so you can use this code. This is just for performing inference on a single image, okay? So I'll just run the code to show you how simple it is. Let me, so the code is, I am using a pre-trained detection transformer with ResNet 50 backbone from Facebook. So I'm just directly downloading this from PyTorch. And I have just uploaded some random screenshot. Actually, I can do it. Let me do something like this. So let's say this is my image and I want to run my inference on this image. So just take a screenshot, then upload it here. During the inference, there will be no ground truth, of course. Yeah, correct. Okay, it's not getting uploaded. Let me do once more. Okay, so this is my uploaded image. It's a bunch of dots. Then click on the three dots, copy path, and paste it here because this is a different image. And now I just need to run this. It may install some of the missing packages, but it's mostly fast. This code is very fast. So here, after running the inference, we are just writing these extra parts to, using OpenCV, display the bounding box because we need to draw the bounding box on top of the image. So that's the only reason I'm running these parts. But I just want to show you the output. I think this will run pretty fast. Yeah, so this was fast and this is the output. So it has drawn a bunch of bounding boxes and the confidence score is very high. I'm sure this is like, round off confidence score. It's not 1.00, maybe it's 0.99 and something. And interesting thing is, see here, this bench also is recognized. We can specify which classes need to be identified. So it will specifically identify those classes. Here, I don't know why tree is not identified. Maybe this is a pre-trained on Coco dataset. I'm sure tree is part of Coco dataset, but I don't know why it's not getting identified. Maybe we can do something else, street. Or people. So now let's see if we put this, whether something will work. Yeah, so you see now everything is getting detected. So we can also specify which objects we need to detect. If you don't want to detect traffic light, if you only want to detect person, it's possible. But the original Coco dataset, if I remember, has only 80 classes. It does not have more than that. So every single object in the world cannot be detected. But bus is getting detected with very high confidence, bicycle. So it's very, very good. So just try out this code. It's fairly easy to run the inference. Even in the paper, they say inference can be run in like 50 lines of code or something. Somewhere they mention in the paper. I do plan to put a paper reading video for this particular detection transformer paper. Is the input resolution dynamic? Yes, input resolution is dynamic. Inference, no GPU is needed for this because it's a lightweight model. I don't think it's more than few million parameters. I haven't calculated it, but my feeling is it's not that big of a model. I want to show you one more thing. This code might be slightly slower, but this is equally interesting. This is for video. So you can run the inference on just like how you do on images. You can run it on different frames and you can display the output of those frames. So let me just reconnect here. And I have a bunch of stock videos here like this. So I'll share one video with you, which you can also use. Yeah, I guess this one. So I'm just pasting a stock video on your chat. So just find the video from there. This code, let me share with you. It's mostly the same. I mean, there is no difference. It's just that for annotation, printing the annotated frames and then downloading the whole uh, frames as one single video, you just need to do something. That's all. But that part is very easy. And I'll just show you while this code is running how the output look like. So original video was something like this: a person walking and then slipping and falling. Can you see the video actually, by the way? I'm not sure if you can see my screen. What all things from my screen can you see? Can you see the screen? Did you see the video of the person falling? Just to confirm if you did not. Okay, okay. Did you you saw the Google Colab code, right? I just want to make sure that can see the notebook. Okay, sure. Let me reshare the screen once. Okay, how about now? Can you see a bunch of things? Can you see this video? Okay, awesome. So this is the video. So I'm running the inference code, which should not take any time to get finished. But because this video has few frames, it will take more time than the other one. But I'll show you the annotated video. So this was the output annotated. So it has annotated bunch of objects that it detected. So it's pretty cool. So that is, yeah, and this code also has finished. So you can basically copy paste any video and then the annotated video you can download from here. So it's very cool. One thing you should definitely try is asking the model only to output certain classes, not every single class. I am currently printing every single class, which is why the videos are looking very ugly. But I want to show you some videos that I have worked with in the past, like some of these. When you annotate, it's very cool actually. So this was not using detection transformer, by the way. This was using YOLO and other models, but it's very cool actually once you annotate specific. So here people are not getting annotated, only vehicles are annotated. Then here, this is on a conveyor belt with bottles. You can annotate and count the bottles. This can be actually done using detection transformer, but we'll have to use some faster models of detection transformer for getting real-time output. This is another cool one, which was again using not detection transformer. This was also using YOLO, but you see the idea. This can be exact same thing can be implemented using detection transformer also. There was one more. Yeah, this is detection plus poster annotation using MediaPipe, Google MediaPipe. So there are a lot of things that we can do with object detection in general. It's like a very interesting area of, there is a lot of industry interest. Oh, did you not see the video which played the basketball video? Did any of you see? I just want to make sure. Okay, awesome. And did you see the what was the second video? The football something that also you saw, right? Okay, awesome. All right, guys. So just try running this code. The inferencing on image is very fast. Inference on video, I'm sure may take maybe 1 minute, 2 minutes. I shared the code in Slack in the chat, right? Did I not? Okay, I'll share this. Yeah, this week there will be. I'm yet to post a Swin Transformer assignment. I deliberately did not post it last week so that there could be a big break. But I'll post it this week. Then videos, I don't have any link because I downloaded it. I can share some videos when I'm posting the assignment. I can share some videos there, so you can take that. But otherwise, I'll tell you some places to get the videos from. Stock videos can be found from Pexels. That is one way. And just for educational purposes, you can just take the videos from YouTube. Like you can download it from YouTube itself. Collab notebook link for DETR, I posted it. Yeah, these are the links. The two links I had posted. For Q&A post link, I don't have it handy right now, but I can post it on Discord. I'm sure somebody has it sampled into frames. And then, yes. So video gets sampled into frames, and frame by frame is how this works. So you might have seen that real-time detection models have frames per second, like number of frames you can process per second for YOLO and all is like 150. For some faster models, it's like 300. Even I have seen models with 500. So if frames per second is 30 or more, then you can call it as a real-time detection model almost. The vanilla version of the detection transformer is definitely not about 30 frames per second, which means it is slower than real-time. But there are other versions which are faster. So in assignment, I think maybe I'll ask you to do inference using one of those models. But it's an interesting architecture, detection transformer, because it's not that different from all the other things that we have learned. It's just that there are a few, Hungarian laws is maybe the only completely different thing. Position embedding is slightly finicky, but other than these two things, I don't think there is anything specially difficult in detection transformer. Swin transformer was different; it had so many different things. Detection, I think it's an okay model. It's not a difficult model. Coding also will not be that difficult in my opinion, because you have repeating modules. You can just easily write that. Hungarian laws has already predefined functions, so we don't want to reinvent that from scratch. But training is a pain. It has to. In the paper also they mentioned that the compute required for training is a little bit longer. But I'll see if I can find a very poor quality data set, like small subset of data set from somewhere where I don't use, because first of all, I don't want to use pre-trained model. I want to use train from scratch, but I can't train on Coco dataset because that is a bit bigger dataset. Then I was trying with RoboFlow, some custom datasets from RoboFlow, smaller, like 100 images, 500 images. Still, the accuracy was very bad. So let's see if something, because if you don't see any good bounding in a box rectangle, it's very disappointing. After, if it's classification, it's okay, you get some prediction, but if you always get no object prediction due to your model being very bad, it's very disappointing. But we'll see. I'll communicate with you. But anyways, thank you so much for listening. We'll meet again next week and try out the assignments. I'll post the assignments by Monday. So thank you so much. See you next week. Bye.